Hi everybody, welcome back to the Feynman Technique. I apologize that I haven't made any videos recently. I've been pretty busy, and I don't make any money off of this channel. Um, so I have to do it all in my spare time. But anyway, today we're going to be deriving the relationship between the beta and gamma function. And we're gonna be doing it not really in the standard way. The standard way you would create substitutions with a double integral that require use of the Jacobian. This is going to involve only single variable substitutions, and I think that's a lot easier to follow for people with only a background up to maybe calculus BC. But anyway, let's go ahead and get started. So the first thing is I just want to define this, and I'm going to be using the notation g of z for gamma. I don't know how to input the actual gamma character into Desmos. So what we're going to be basically saying is this, that gamma of z is for the most part equal to z minus 1 factorial. That holds for, I believe, integer values of z greater than or equal to 1. Um, but the gamma function basically extends the factorial like this. Gamma of z is equal to z minus 1 factorial. All right. And from many previous videos, I've shown this in a lot of videos. This is true. If you take the integral from 0 to infinity of x to the n times e to the negative kt dt, I use different variables in my previous derivations, but this is what you end up getting. You get n factorial over k to the n plus 1. Now, extending this, um, we can say this. If we let our n equal z minus 1, we just get this relationship. And the relationship we're really after is this. This is kind of an extension of the gamma function definition. It adds this. Normally, there would not be a k here, and we would just end up with this thing equaling gamma of z, where that k is equal to 1. But the extended version of that is this. And we are interested in this being equal to this. Okay, so next. Again, now we're really just defining gamma of z. And all I did was take this and set k equal to 1. So this is gamma of z. And don't forget, what we're trying to prove is this. This is the beta function in terms of x and y. And it's equal to gamma x, gamma y over gamma of x plus y. Okay. So now we have our definitions. And now I'm just going to restate our original goal right here. We're trying to prove the relationship between the beta function and the gamma function. All right, now to start off with, we're going to make a substitution. Our substitution is going to be u is equal to t over 1 minus t. Now, this isn't actually where I started. Really, I started with this substitution, that t is equal to u over 1 plus u. But it's easier to see what our bounds of integration are going to change to if we leave it like this. Our new variable u, let's see, when t is equal to 1, we're going to get 1 over 0, which is infinity. And if t is equal to 0, we will end up with 0 over 1, which is 0. So our bounds of integration will change from 0 to infinity. That's why I wrote this. This was the original substitution. I want to make t equal to this. Okay, that implies that u is equal to this. So I have t in terms of u and u in terms of t. All right, so that implies that our term 1 minus t, just do a little bit of algebra, and that's going to turn into this. And finally, our differential dt is going to transform to 1 over 1 plus u all squared du. Okay, so let's plug that substitution in. Let's perform that substitution. Now, just copying the things directly, this is what you get. All we did is literally replaced our t with the u over 1 plus u. That's right here. We replaced our t with that, our t right here. We replaced our 1 minus t with this right here. Wait a second. Well, actually, I just replaced the t with it, it looks like. But what I should have done is actually replace the entire 1 minus t with 1 over 1 plus u. But I believe we do that in the next step. And then I just replaced our dt with this. And the next step is the simplification. It actually simplifies to this. This whole integral right here, you know, you've got to do some tricky algebra, but it will simplify to this without too much trouble. Okay, just use the properties of exponents, combine like terms, and you will end up with this. Okay, so well, here we are. So where are we going to go? Where are we going to go from here? Well, I'd like to bring up this previously defined thing right here. We previously stated that. That's somewhere up here. I believe it's right here. Okay, now let's see. This means that if we take this and set it equal to this and just cut out the middleman right here and divide both sides by gamma of z, we end up with this. Now our goal right here is to match this with this. Okay. So if we take this right here and replace our z with an x plus y and our k with a 1 plus u, we just end up with this. And don't forget, this is exactly this right here. So we can replace this, this denominator right here with this expression right here. And that might seem like it's making it a lot messier, but good things are gonna happen. So let's see, let's just copy and paste that over here. Again, you'll see all I did was replaced this, which is a 1 over 1 plus u to the x plus y, with this. That's all I did. So this is what we have. This is what we have after we sub that in, unmodified. Now what we want to do is we can bring out this gamma 1 over gamma x plus y outside of the entire thing, since it doesn't depend on t or u. And also, both our bounds of integration are 0 to infinity, and there are not going to be any convergence issues, so we can play around with the order of integration all we like. Okay, so after we do this, this is what we get. So I made it a double integral, and I brought all of the terms inside one single integral with respect to t. So this is our first integral that we need to evaluate right here. Well, since it's with respect to t, that means we can just bring out anything that does not have a u in it. Well, actually, first, I believe what we're going to want to do is switch our bounds of integration, or our order of integration. We're going to switch this dt and the du right there. And there's no problems with convergence, so we can do that. Okay, so as you can see, that's what I did. Sorry. Yeah, you can see that's what I did. I just switched the order of integration. Now, since we're integrating with respect to u here, we can bring anything that does not depend on u outside the integral. And that's what happens. This is the exact same expression, just I brought everything that does not depend on u outside of the integral. And now you'll notice this is very similar to something that we previously derived. Don't forget, we already showed up above that this is true. So that means that this is true. We replaced our t with a u, we replaced our z with an x, and we replaced our k with a t. So this is true. And that is right here. So we can simply replace this with this. And that's what I do in the next step. So now we have this. All right, great. Well, you'll notice a bunch of things happen. We have a t to the x here, and we have a t to the x here. They're going to cancel. Also, this gamma of x is going to come right outside. So in the next step, we have this, and this should be instantly recognizable by now as gamma of y. So finally, we have this. Beta of x and y is equal to gamma of x times gamma of y over gamma of x plus y. And that's a very useful formula. Hopefully I'll be doing some integrals that involve that in the future. All right, guys, hope you enjoyed that, and we'll see you next time.